Okay, so welcome to part 2 of this video in which we are tackling a problem in conditional expectation, which will use linearity big style. Okay, what we have, this is the setup, we have 15 committees and 100 people, and we are ascribing the 100 people into these 15 committees. So each person goes on to 3 committees, and each committee can only take 20 people, okay? So there are loads of possible ways that those 100 people could organise themselves so that that setup is obeyed. And basically, we've said we've made this probability space, and then to make the boundaries more clear, I'm going to highlight them. We've made this probability space which contains every possible way of ascribing these 100 people into these 15 committees. Okay, what we're trying to prove is that at least one, at least one intersection of these committees. So if you pick, if there are loads of possible ways that you can intersect these two committees. So you can ask, what's the intersection of 1 and 2, which means which people are on both 1 and 2. Basically, what we're trying to show is that at least one of the intersections, one of the possible intersections of these 15 committees. So you pick any 2 here, and basically, of all the ways that you can pick 2 committees and intersect them, at least one of them the intersection will contain 3 people. So we've then said, okay, let's store the information of how those 100 people ascribe themselves into those 15 committees, and let's turn it into a different form. Let's instead store it in the form of these balls. Now, instead of representing the individual committees, they represent the intersections of the they represent every possible intersection of of 2 committees, or 2 of the 15 committees. What we discussed in the previous video is if you have all of this information of which people are in, which of the 100 people are in each of these intersections, you have all of the information here. So each one of these has a unique one of these, and each one of these represents a unique one of these, basically. So they're just equivalent ways of storing the information. Okay, so now I've got this same probability space, just we're representing these possible outcomes, possible ways of 100 people organising themselves onto 15 committees, such that everyone is on 3 committees and every committee contains 20 people. We've got it all stored in this specific way, basically. Okay, now what we're going to say is we're kind of going to initially the way we were viewing it is we were viewing this all of this information as being a single outcome in this probability space. Now we're going to sort of get rid of these boundaries here, and we're going to make the probability space contain absolutely all of these intersections for all of the outcomes. So basically, I'm going to promote these outcomes to being events, the events that you choose, that way of ascribing the 100 people. So now what we're going to do is basically I'm going to break down what I'm highlighting in green now, these green lines. I'm going to break them down, and we're going to view the probability space now as being this space containing all of these intersections with certain people in, basically. Okay, what were we trying to prove again? We were trying to prove that there is at least one intersection of committees which contains 3 people. So we were trying to prove that for any one of these outcomes, whatever one you pick in this probability space here, whatever one you pick in this probability space, at least one of these little circles here contains 3 people. So here's going to be our action plan. Here's how we're aiming to prove this, and I'm going to show you why letting the green lines break down is going to help that in a moment. Okay, so here is our action plan. If we can calculate the conditional expected value, so if we can calculate the expected value of the number of people in each of these intersections, and we can prove that it is, if we can prove that it's greater than 2, then we're in business. Let me explain why. If you get an expected value for basically what we want to do is we want to calculate the mean. So we want to sum up all of the people in this intersection, all of the people in this intersection, all the people in this intersection, want to sum it all up and divide through by the number of intersections, 105, for an arbitrary point in this. So we want to say, okay, pick an arbitrary way of ascribing these 100 people into these 15 committees. So pick an arbitrary outcome in this probability space where we're viewing the green lines as still existing. So an outcome at the moment is one of these entire rectangles containing all of these 105 circles. If you can then show that if I average out the number of people in all of these circles and take the mean of them, basically, so if I add up how many people are in this one, 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 out how many people are in this one, and then divide it by the number of them, i.e. 105, that will calculate you the mean number of people in each of them. If I get a mean that is 2.2, let's say, that would imply instantly that there was at least one of these with 3 people in. Because suppose the only other options, if there's not one of them with at least 3 people in, then all of them would either have 0, 1, or 2. So those are the only options for how many people can be in each of these. If all of them contain 0, 1, and 2, then you could not possibly mean out a bunch of values which were 0, 1, and 2 and get a value of 2.2. You can't. The mean will never be above the maximum value that the variable can take on. If it can only go up to 2, then the mean cannot be greater than 2. So if you get a mean greater than 2, it instantly implies that one of these must have more than greater than or equal to 3 people in. So that's going to be our battle plan. We're going to say, okay, let's find the expected value of the number of people in each of these intersections in here, and then if that's above 2, then we've done, basically. Okay. So why did I say let's assume that these green lines are breaking down? Well, the reason is that it's easier to think in terms of that, to find the expected value of this random. To find the mean, it's actually easier to think in terms of that breaking down, and I'll show you how. So I'm going to show you how we're going to calculate that mean and prove that it's over 2. Okay, so we're going to think about setting up a random variable, big X, and this is why it's important to think about the green lines breaking down, because now this random variable is going to act not on these entire sets of 105 circles, but it's going to act on each of these individual circles on themselves, which is why we need to think about the green lines breaking down, basically, and think in terms of the probability spaces containing every single one of these intersections as a plausible outcome. If you like, you can label each of the original outcomes, i.e. each of the ways of ascribing 100 people, ascribing 100 people to these 15 committees such that every person is in 3 committees and every committee contains 20 people. You can think of labeling each outcome with a symbol, if you like. So let's label this one phi, this one phi, or you could just be sensible and label this one 1, 2, 3, 4. So something to distinguish them, so that this circle here, which is 1 intersection 2, and this circle here, which is also 1 intersection 2, don't get confused, because this is 1 intersection 2 corresponding to this first way of ascribing 100 people to 15 committees, and this is 1 intersection 2 associated with the second way of ascribing 100 people into these 15 committees. So basically, don't think that, are these all now going to be viewed as the same thing now? No, just label them with a different symbol, basically, to denote which original way of ascribing 100 people into 15 committees they belonged to. But now, our outcomes in this probability space are the individual circles now. Okay, and this random variable is going to map each individual circle onto, well, it's very simple. It's going to map it onto a real number. In fact, it's going to map it onto a non-negative integer. so we'll just put integers there, but it's actually going to map it onto 0, 1, 2, 3, 4, and you should therefore be able to guess what I'm going to make this random variable. X is going to map a circle, so I'll draw a circle, 1 intersection 2, let's say, for example. In fact, I'll just put circle there. It's going to map circle onto the number of people within that circle, within that intersection. Within that intersection. Okay, so that would be great. So what we're trying to work out basically is we're trying to work out the expected value of this random variable where we condition on we're not trying to work out the expected value for the entire probability space. That's not what we're trying to do. We're trying to say if we assume one of these has happened, but we don't know which it is. That's the whole point. We're going to keep it arbitrary. We're going to say, okay, we're just assuming one has happened. We don't know which it is. Just say it's an arbitrary one of these possible ways of ascribing 100 people into 15 committees. So say one has happened, then find the expected value of this random variable on that arbitrary way of ascribing 15 people into 100 people into 15 committees. So that outcome in the bigger probability space, the bigger outcome, if you like, which is now unfortunately being promoted, you might think, to an event rather than an outcome. Okay, so that's what we're trying to work out, and that's why this is going to be useful, right? Okay, so we would like that conditional expected value. But this isn't very easy to work with, basically. We can split it up, though, into a sum of a bunch of other random variables, and then use linearity is what's going to be brilliant. We can think of this as being the sum of a bunch of other random variables. So let me define a bunch of other random variables. Let's define x subscript 1 to again be a random variable, which now is Bernoulli, and is going to map you onto either 0 or 1, and it's going to map each circle. So each intersection is going to map onto either 0 or 1, and it's going to map you onto 0 if person 1, so if I'll draw person 1 here with his banner 1, is not in circle in your intersection, and it's going to map you onto 1 if person 1 is in your intersection. 1 is in your intersection. Okay? So you can then imagine what we're going to do to generalize this. We're going to make a random variable x subscript 2, x subscript 3, x subscript 4, all the way up to x subscript 100, and they will be mapping you onto 0 or 1, depending on whether you contain, whether your intersection, you as a little intersection thing here, contain person I, let's say, where I is between 1 and 100, or you don't. Okay, so we need some more paper now, and I should go over the back, but I don't really want to lose my picture. We'll go on to the back. Right, so I'm going to have to redraw out the picture. So here's our setup then. So this is our probability space here, with our each of these outcomes, each of these ways of ascribing 100 people into 15 committees, stored in this specific way where we tell you what's in each intersection, basically, rather than who's in each committee. Okay, so here you go. Now we set up a random variable x, which is going to, instead of we're now not viewing we're not viewing this now as being this green thing, this green rectangle, all the information. We're not viewing all the information regarding how you've ascribed these 100 people into the committee as being an outcome anymore. We've promoted it to an event. We're viewing how many people there are in each of these intersections as being the outcome now. Okay, and x is going to map each of these onto the number of people in it. So it's going to map it onto an integer. And we've set up a new random variable, x1, which is going to map each outcome. I mean, I just want to draw another possible way of ascribing 100 people into the 15 committees, just to emphasize that there's more than one. Okay, and this is now going to be a Bernoulli random variable, and it's going to map you onto 0 or 1, depending on whether you contain person 1 or not. So if you contain person 1, it will ascribe you a 1. If you don't contain person 1, it will ascribe you a 0. We then set up x2, which again will map you onto either 0 or 1, and each of these intersections it will map you onto 0, it will be mapped onto 0 if it does not contain person 2, and will be mapped onto 1 if it does contain person 2. Okay, and we'll go all the way on to x100, so there are loads of them in between there, which is again a newly random variable ascribing you 0 or 1, and it will ascribe you 0 if you do not contain person 100, and it will ascribe you 1 if you do contain person 100. Now, hopefully it is pretty obvious that the random variable big X is the sum of all of these, because if you contain each of these people from 1 to 100, it will have ascribed your 1. If not, it will have ascribed you 0. So if you add them all up together, the number of 1s you add up will give you your value X, because the number of 1s you add up will be the number of people that were in your intersection, basically. So it will ascribe you, that value you get when you add up those 1s will be the same as the number of people in your intersection, basically. So that is a useful thing to know. Okay, now we want to know how are x1, x2 to x100 distributed, because we want to work out what the expected value of these are, conditional on a single outcome having happened, so that we can then work out the expected value of x by linearity of these, by linearity. Okay, right, so the first thing to note is that obviously these are not independent, because if you do have each committee can only contain 20 people, and therefore each intersection at the very maximum can contain 20 people, because if it contained more than 20 people, that would imply that more than 20 people were in committee 1 and more than 20 people were in committee 2. At the very most extreme, you can have the same 20 people in committee 1 and the same 20 people in committee 2, in which case their intersection contains 20. So these cannot possibly be independent, because if there are 20 people in if the first 20 random variables up to x20 were all 1s, then that would force the other 80 random variables to all be 0, basically. So they're not independent, but we know linearity of expected value doesn't require independence, so that's not too worrying for us. Right, what we want to know is how they are distributed. So what we would like to know is what's the probability that any single intersection here will be ascribed the value 1, basically. What's the which means exactly what is the probability that any old intersection is going to have the person 1 in? And the first thing to note is that absolutely every single one of these has an equal chance of having person 1 in. There's no reason why 1 intersect 2, this one that I've drawn right at the left, should have a better chance of having person 1 in than the one right over here. They all have an equal chance of having person 1 in. So overall, this random variable is going to be a constant, basically. Well, its probability. The probability of you getting a 1 is just going to be the probability of a single one of these having person 1 in them, basically. So what we want to know is what is the probability of having a single person 1 in let's say, just for argument's sake, let's say in 1 intersect 2. And we know that the probability of it being in 1 intersect 3, 1 intersect 4, etc. is all going to be the same. So that will be the probability of you being a 1, basically. Okay, so what is the probability that you're in 1 intersect 2? Okay, well that means that person 1 would have to be in both committee 1 and committee 2. Okay, but how many possible ways are there that person 1 could choose? Well, how many possible ways? Person 1 has a bunch of ways of choosing which committees he wants to be in. How many possible ways are there of describing just person 1 into 15 committees? So if we want to work out what's the probability of person 1 being in both committee 1 and committee 2, what we need to work out is how many ways are there of describing person 1 into he's got to be in 3 committees. And of those, how many of those ways satisfy our condition, i.e. that person 1 is in both committee 1 and committee 2. So firstly, the total number of ways of ascribing him, the total number of possibilities are, he chooses his first committee that he wants to be in. So there's 15 possible choices for his first committee that he wants to be in. His second committee, he has 14 possible choices because he's already chosen one, so there are 14 left open to him. And then finally, for the third one, there are 13 possible choices. But again, that is going to count the fact that if you choose committee 1 as your first committee, then committee 2 is your second committee, and committee 3 is your third committee, that's going to be counted as a separate option to if you choose committee 2 as your first one, committee 1 is your second one, and committee 3 is your third one. We don't want that. That's just silly. We just care about what committees he's chosen. We don't care about what order he actually picked them in. We just care about which ones he actually chose. And to take account of that, what we have to do is divide through by how much we've overcounted, which is all the possible ways, all the possible orders that you could have picked any 3 committees in, which is, you could have picked, there are 3 possible things that you could have picked first, because you've picked 3 committees, so there are 3 possible choices for which committee you picked first, there are 2 possible choices for which committee you picked second, and there's 1 possible choice for which committee you picked third. So that we'll divide through by that, and that will give us the total number of ways, the total number of possibilities, the total number of possible combinations of 15 committees that person 1 could choose to be on. Okay, so how many of these satisfies the condition that person 1 will pick committee 1 and committee 2? So now what we're doing is fixing. We're saying, okay, person 1 has picked committee 1, so we've got this one. Person 1 has picked committee 2. What then? Well, there are 13 possible options then. He just has to pick one more. That's it now. It doesn't matter, because he's only picked one. He's got to have 1 and 2. So there are 13 possible choices, possible different choices of possible options of committee choices that he could pick, such that he has picked committee 1 and committee 2. So he could pick committee 1, committee 2, and committee 3. He could pick committee 1, committee 2, and committee 4. He could pick committee 1, committee 2, all the way up to 15, and there are 13 of those. So the probability that he's on committee 1 and 2 is 13 over the total number of possible ways, which is 15 times 14 times 13 over 3 times 2. Okay, so firstly let's cancel those 13s there. Then let's cancel the 2 with the 14 to make 7. Let's cancel the 3 with the 15 to make 5. And then overall what we're left with is 1 over 5 times 7, which is 1 over 35. So the probability of getting a 1, i.e. the probability that person 1, the probability of the random variable x1 ascribing you a 1 basically is going to be 1/35. So x1 is Bernoulli distributed with probability of getting a 1 divided by 35 basically. Okay, right, so now what's the difference between person 1 and person 2? Absolutely nothing. I'm not saying you ascribe person 1, you put person 1 in first. I'm saying you just put person 2 in. We're not talking about forget this discussion of independence. I could have put person 2 in before person 1. So there's no difference between person 2 and person 1. So basically what I want to say is all of these random variables are identically distributed. They're all distributed Bernoulli 1 over 35, because the probability of any one of these intersections in here having person 2 in is also 1 over 35. It's exactly the same, and again it continues on to x 100, which is also Bernoulli distributed. So they are all identically distributed. They are, however, not IID, which stands for independent and identically distributed, because they are not independent. Okay, right. So we'll call a break there, and we'll continue this discussion in the next video.